Hola, Barcelona. I'd like to take you on a journey into the world of data engineering today. My name is Alexander Günsche. I'm a senior solutions architect at AWS. And I'd like to go with you about how to build and maintain and manage a serverless data lake on AWS. So why do we need this kind of technology anyway? Because it's very different from what you may be used in areas like Kubernetes or general backend engineering. And the reason is that you probably have perceived yourself that the amount of data is growing. And it's not growing linearly, but it's growing exponentially. Based on a study by IDC a few years ago, it is growing by a factor of 10 every 5 years. So the data systems we are building today need to work with a capacity that is 1,000-fold to what you have today in 15 years. And as we know, systems tend to live for that period of time. So the technology we need to use here needs to be purpose-built for these amounts of data, for terabytes in total volumes, and for gigabytes that you process with every transaction. At the same time, data goes stale very fast. And depending on what you need to do with data, you need to be aware of this. So some data purposes need to happen in real time. And this is mostly in the area of observability that you mostly are familiar with, I guess. There's data that needs to be actionable, so very little delay or latency between getting the data and working with it. But there's also data purposes that are more in the space of reactive or even historical analysis. And you might think this is not relevant, but the thing is, it is highly relevant for things like business intelligence. This is what organizations need to make data-driven decisions, to look at data over a long period of time, not necessarily in real time, but huge amounts of data, very complex data, correlations of data from different domains. And this is what we're going to talk about today in terms of the purpose of what we're doing. At the same time, you will not do those things in the real-time transaction systems that you have. So typical data analytics happens in dedicated data systems that get data from your sources. And we will see in a second what that means. And data systems and data analytics tooling is not just one tool that you have that solves all your problems because of the different applications, the different roles, the different consumers in your organization. But you will see that you have traditional databases, you have machine learning applications, you may have data warehouses, and we will have a technology more and more coming into play in these scenarios that is called a data lake. Who of you has heard of a data lake, or maybe even worked with one? Okay, quite a few, that's nice. So we're going to see how we can build a data lake in a serverless manner so that you reduce the burden of infrastructure management. I will show these examples on AWS technology, but I will also make sure to explain the underlying concepts so that you can transfer them to other domains. I will name a few open source tools that you can use, and then ideally you can try things out and see what works best in your scenario for your organization, for the tools that you have at your hands. So let's go into the fundamental building blocks of a data lake. What do you take? Again, this would be based more on AWS in this presentation. But thematically speaking, you would have your data sources already mentioned. This can be transactional systems like your, let's say, e-commerce databases. This can be technical data such as logs. And this can be IoT data that you get from the machinery and industrial applications around your layout of the organization. And the data from all those sources will come together in an ingestion mechanism. So a transfer mechanism that takes data from those sources and brings them into the scope of your data lake. There are different types of ingestion. We, for example, could do batch ingestion, where we, let's say, copy large chunks of data periodically into the data lake. Or what we will do today is stream ingestion, where we'll look at how to use a streaming mechanism to make that transfer. Once we have transferred the data, of course, we need to store it. We talk about extreme largely amounts of data, as I mentioned, typically terabytes, more or less, sometimes even petabytes. And we need to have effective mechanisms to keep the data, retain it, then, of course, also to process it in a way that it becomes useful for analysis, and then, of course, expose it through data access layer. What we need around this building block, or these building blocks, is of course, we go into the consumer space, and that is where you have applications like business intelligence, or machine learning, or other consumers that work with the actual data that you have prepared for that purpose. But the entire data lake needs a layer of governance, because just simply storing data, processing data does not give you visibility, does not give you security and governance. So it is very important to create that around your lake as well. So when we go through those building blocks and see what you can use in order to build your own data lake, we will start with the data stream. In this case, again, batch ingestion would be an alternative, which we'll not discuss today. So for those of you who haven't worked with data streams, what is that? Stream, the term stream might suggest that there is a constant flow of data going through one system and coming out in somewhere else, but that's not really the case. That would be misleading. What you do have in the beginning is a producer of data, obviously, where large amounts of data will be produced in a continuous manner. And this will then, of course, be put into the stream. But what is the stream internally? First, a stream is not unlimited. A stream has limitations. And to address the physical and infrastructure limitations that streams typically have, you have so-called shards, so-called compartments, if you will, of the capacity of the stream, which allows you to scale horizontally without having a completely overflow of one unit in this stream. So you still have a mechanism to parallelize things. In those shards, you have so-called records. And these are data objects that come in, for example, a log entry or a transaction from a database, an IoT signal of some sort. And these records stay in the stream. It's not like they're being pushed out or immediately kind of forward to some consumer. They need to be pulled from the consumer. I mean, depending on implementation, it may feel like a push mechanism, but technically speaking, you are pulling that, and you are pulling it from an iterator. So you can see the stream as a sort of buffer, if you will, and you can reference the records in the stream. And unlike traditional event mechanisms, where the event is the unit of work, the stream itself is the unit of work, and you will process chunks, you will work on a stream, you can move forward, and then get one or batches of records into your consumer. So a popular streaming service on AWS is Kinesis. You could also use Managed Kafka, or Kafka in general is an open source that you could use for this purpose. But let's see how Amazon Kinesis would work in such a scenario. So again, you have different types of producers, IT sensors, enterprise applications, and so on. And then they would be put in the Kinesis data stream. I'm emphasizing data streams because there are different types of streams or services in the Kinesis family. What we're using here is data streams. And then we could have different kind of consuming mechanisms behind that data stream. So again, thinking about the different scenarios that you could use in order to create, let's say, real-time information systems, you might have data analytics from Kinesis as well. You could have it in another stream. Then you would use Kinesis Firehost to actually bring that into a consumer, and then you could have an open search dashboard. I'm not saying you should do that. If you do it for the wrong purposes, with the wrong amount of data or data frequency, you pay a lot of money without getting a lot of value out of that. It's just an example how that could work. Now, for near real-time data systems, you could use something simple like another analytics stream where you can, let's say, process the data on the fly and then forward it to a notification mechanism, just like Amazon SNS. But what we are going to discuss today is actually long-term storage and analysis toolkit for business intelligence. And so what we're simply going to do is be using an Amazon Kinesis data stream together with Firehost, which is basically a mechanism to push data into a consumer, in this case an S3 bucket, without you having to actually scan the stream and do all those things that I've been talking on previous slide. So this is so-called, so to speak, a front end that just pulls it out of there and forwards it. So now we have data, or now we are putting data into an S3 bucket or some other storage mechanism if you want to run this yourself somewhere else. What do we do with it now? So the way we put data in this bucket or storage mechanism is a series of JSON objects, let's say in this example. And it would be, in most scenarios, something where you have a so-called JSON-L file, so a file not with one big JSON object, but multiple lines of JSON simple events. But you could also have other types of data, depending on use case, and that's the nice thing about the data lake. It can deal very well with unstructured data. So actually, you could also put PDFs in there or images. So if you happen to take images of your machinery for, let's say, machine learning purposes, for maintenance, let's say, and predictive maintenance, then you could have images there that you could later process. But still, the data now at this point is not very well suitable for analytics for two reasons. First, it is still in a format that is not very well readable. Again, think of huge amounts of data, and now imagine you would have to parse through lots of JSON files or JSON-L files and read and parse the JSON structure. And secondly, it is still the domain logic of the producing system. So what we need to do is transform this data in a way that it is optimized for the queries of the intelligence system. And this is where we first put the data into a certain format and then allow transformation jobs to run over that data. So the first thing when you store the data in this bucket is you will follow a certain convention that you see up here. And that is a structure that consists of well, in a S3 case, it would be an S3 object name. If you have a block storage, it would be folder names plus file name, but it's basically the same in practice. But you would always start with something that's the base name of your resource, obviously. But then it's important that you would use a table name. And the table name is not what you know from transactional systems like a SQL database table, but you should see it more as a data domain or a data scope. Secondly, you will store the file in the structure of several partitions. And you see here that these partitions are stored in a format that is a key value pair. This is very useful in these big data scenarios to pre-partition the data and scope it to certain analytics scenarios. Let's say I would only want to analyze the data from a certain period of months. Then I don't have to go into the lake and scan for all the data at the same time, but I can limit it to the folders that have, let's say, a yearly or monthly or daily structure. And finally, I would have the data file itself, and you would have this in this scenario by the hour. I should note you can use other partition types as well. So if your data is not so much a time series logic, you might use this with other kind of dimensions that help you pre-structure the data already in the access structure. Now, we have to do the first transformation of the data, and this is one that allows us to better read and scan the data. Again, we currently assume that we have this data in unstructured or a plain text format. And what we want to do is, we want to do it in a format that is write optimized first, because we need to shovel this data over, and it will also be optimized for reading a bit better and pre-curated. So, for example, if you have an image, we could already run some sort of ML algorithm over it. The storage format for this data is a binary format. And we can do this with a tool like Apache Spark. So you may have seen or heard about this. This would be a tool that can help you with transformations or kind of taking a data set and bring it into a different structure in a different way. And if you are in the AWS world, you can use AWS Glue, which is a family of services, but in this particular case, it would help you with managing those transformations for you. The file formats that we use here, as I mentioned, are binaries. So you, instead of the JSON-L file, you would transform this into one file that contains the same data, but you could imagine this as a little binary database blob, so to speak. So you cannot read it or do grep or something on it. It doesn't work. So there are different file formats that can be used here that you will typically see in such a scenario. There's Apache Avro, which is a row-based format. So you still have your entries line by line, but it's a binary format which is much better accessible. Secondly, and this is one of the most popular in this space, you will see Apache Parquet. This is also binary, but in this case it's column-based. And it's much better optimized for read access of your typical analytics cases. You will also hear, so if you're working on this space, you will see more frequently tools like, file formats like Iceberg, which is kind of a newer way to build data lakes overall. So I'm just mentioning it here in case you come across it, but I should note that it is not in the scope for today's approach. It's a transactional data lake. It's a fun as well, but it will not fit into that paradigm we're discussing today. So what you will typically see in these kinds of data lakes is Avro, or even much more so Parquet. So now we need to do a second transformation. This is not a structural transformation, but a semantic one. So imagine we have a data object, and this data object contains, let's say, an e-commerce transaction, and has the domain logic that is coming from the producer system. So you see here an ID, a user object, you see a list of items that represent an order. But let's say in your business intelligence system, you need this to be flattened, you need some data to be removed because it's just redundant or unused and saves money if you don't store them. So what you will do is you bring this into a different format. And you will not spot many differences if you just look at this, but here's one, for example. We have pulled the user object out of the previous object and have removed personal identifying information here. So this only has a user ID and the city because we need it for analytics. We could also have some sort of hash to make it identifiable, but it's anonymized. We don't have the name here anymore. And as you also see, there's an order total now. For example, you would want in your analytics tool to see the total order value, and you do not want to calculate it every time again from the items when you run analysis. So we're already doing that here. So again, this is something that Glue will do for you in basically a little Python script that you can use in order to run these transformations in your pipeline. So what we have now is here a three-tier data lake architecture. So you've seen already earlier, we call those buckets bronze, silver, and gold. And we are using this pattern basically to curate the data, to optimize it for read access, to remove unnecessary or even harmful information or information that shouldn't be there. And we can even aggregate it with other sources of information in order to be most useful for analytics. So this is now the core of your data lake, and this gold bucket you see here is the source of data that you will run against in order to run analytics. And we will see in a minute how that works. But before we go into that, a word of warning. So again, you have a lot of freedom to do these things in the way that suits you best. But please don't be tempted to use the tools that you know just because you know them and it's the easiest way forward. We're talking about terabytes of data that need to be stored, that need to be processed, and that need to be transferred to other areas. So be very aware that you use purpose-built tools for that. I'm not saying everything should be on AWS. If you choose so, that's nice. But there's open source tooling that you can use. Of course, you can use more generic hardware for these purposes, depending on the amount of data you use. I would say you can even go to a different cloud vendor. My point being that there are very good purpose-built tools, and in the interest of your organization, make sure that you have cost as a function of your success. Okay? So be purposeful about the compute you use in terms of the cluster. Be mindful of the storage mechanism that you take, and be mindful how you get data from A to B, especially when you go outside of your cloud vendor in order to have a cross-functional analytics case. So now we have data stored. We have it in the format that we want to analyze, but how can we access this data? What is a good way to get visibility is first a metadata catalog. So you can imagine that a bit like a open API specification where you have the visibility of the structure that lives inside your gold bucket. So you would see which entities do I have here, what kind of scalar values do I have sub-objects of some sort, what are the data types of it, and you have some meta information about the recency of data, about the amount of objects there. And this is all what you need to, this is the first building block that you need in order to get visibility at all, and later also to apply security mechanisms on top of that, as we will see later. So this metadata catalog is the layer that gives your consumers visibility, but the mechanism to consume data from your lake would be some sort of query mechanism and some sort of API. So what kind of API could be useful for that purpose? It's actually SQL. This may be surprising because most people would say when talking about APIs, you would have something like REST, OData, GraphQL, And you can use those paradigms, and you can use tooling for that. We come to that later. But in most of these cases, you will run SQL queries. Why SQL? If you think of paradigms like REST, or you think of GraphQL, then they have certain limitations. For example, in the case of REST, the API needs to be specified, so you have to predefine the fields you want to access. You need to know which kind of access patterns you will have at the point of the API specification, and you will have a hard time allowing deeper queries. Of course, you can expose them. Of course, there are ways in REST to specify deeper structures, nested structures, but they also all need to be predefined. It's very hard in REST to define ranges of data that you want to query, so REST is not very well suited. You can build a REST API, but be aware of those limitations. There is a paradigm called OData, which is on top of REST. It's much better suited. Doesn't see much adoption, though. You could, of course, use GraphQL. GraphQL is wonderful for querying structured data. The problem with GraphQL, with these amounts of data, is that it will be very heavy to transform the lake data into a graph. So especially the federated graph, you would need the resolvers that do all the heavy lifting on transforming this into your graph. You can hardly cache anything because depending on the query, there is no recurring pattern. It might be, then of course you can cache a bit, but it will be very, very heavy to expose this data as a GraphQL. So SQL addresses all those things. You can have ranges, you can select specifically the fields you need, you can do joins, you can have conditions on which you want to query data. Now you might say, wow, exposing a SQL interface to my consumers doesn't sound right, because SQL injection, everything. So we'll talk about that later. But the important thing here is it's not a SQL database. It's not a relational database management system, but it's just a query layer that we will allow to access data and read fetch in your lake. And again, there is an open source project that will allow you to do that. It's called Trino, or the predecessor Prestos, maybe something you have heard or worked with. And when you're working with AWS, there's a, let's say, managed version of that with some additional features called Amazon Athena. So ultimately, when you build your lake, you can access the data in that storage facility, in your gold bucket, let's say, through this access layer, SQL-based, and have rather complex queries. The important thing to understand here is it's not real-time queries. So a query against such a big data system could take multiple seconds, minutes, maybe even later, and you need to take this into account when building entire workloads or systems and services that allow you to retrieve data from there. You talk about queries that run against a flat file. Even though it's binary and optimized for read, still needs to connect to the S3 bucket, let's say, or your other storage facility. So that needs to be kept in mind, but the result will be basically a SQL response. So moving on, how can I now build a system that is secure? We have discussed that, of course, exposing SQL to the, well, we're not really exposing to the web, we're exposing it to other clients, but it is an HTTP interface, and so people could theoretically access that. So the first layer of security is obviously authentication. You want to make sure that the people consuming or the service consuming data from your lake through the access layer are identified, and you will use some sort of IAM mechanism. It could also be federated IAM. It doesn't have to be AWS IAM, but it could be some sort of open format like SAML in this case. And you could even do this cross-account or with an external data processing or analytics system. And of course, you can set permissions. In this case, you will use select because that's the only thing that makes sense in this scenario. And so you have your first layer of security in front of the lake. Now, it might be that you don't want to allow every consumer to read the same data from this lake, and you don't want to replicate the data even more. So you already have 3 buckets, that's more than enough. How can I limit that? So first, we can introduce column-level access, and we can say in our data structure that is documented in the metadata catalog, we can now use that to say which of the columns should be accessible by which user. We can separate it, for example, in the multi-tenant scenario to say this tenant has access to those data, that tenant has access to a different set of data. And especially in SaaS systems, or software as a service systems, it might even make sense to have row-level access. So you want to limit the access of data entries to a particular user. Let's say you have tenant 1 is able to access a certain set of rows, tenant 2 another set of rows because they relate to their business. Then you can introduce a filter. Keep in mind, this is just row-level access based on a filtering mechanism that kind of filters results from the query based on the pattern you define. It's not object-based access, so you could not say that a user is allowed to access this object or another object, because by the data change rate and the amount of data you're processing here, it doesn't even make sense to reference individual entities. So you only say exclude results that match a certain pattern. So this is the mechanisms that you can apply to have authentication and to some degree of authorization on your data lake without replicating data per tenant or user. So what would it look like in practice? Now we have all this set up, and you've seen previously we have the ingestion mechanism, we have the storage mechanism, we have some sort of data access layer, and now we want to consume data. How can we do that? So as already mentioned, there are some tools you can use out of the box. So let's say you are a user or a, let's say, client application for that purpose, and you want to run analytics. In this case, you would use some business intelligence service. In this case, Amazon QuickSight, you see the logo, but it could be anything else as well that is able to integrate with that lake through a native integration. And when I say native integration, you could also use some sort of SDK that already abstracts away the implementation details of the API for you, assuming that you want to just connect on a business level. Now, the business intelligence system in that scenario would go first to IAM to identify you. Again, it doesn't have to be AWS IAM as the service, but IAM as a concept, so just to authenticate you. It would then go to the query engine and retrieve data. Some business intelligence systems are also able to cache data themselves, so you can run faster analysis, but that is an internal detail of the business intelligence. And then as it goes from the query engine, it would go to the data catalog to match the query that has been submitted to the actual data that is visible in the catalog. Then if we go to the filtering mechanisms introduced through the row and column-based access controls, the data through the data catalog, you would then again see if that user has permission to access the data that has been requested. And finally, you would go to the data lake, meaning your gold bucket where the data resides. So this assumes that you have a tool that is able to, so to speak the language of your query engine, both semantically in terms of SQL, but also structurally in terms of the integration mechanism that AWS, in this case, provides. What would you do if you have consumers that don't care about any of this? And this would be coming back to paradigms like REST or GraphQL, where you have a very generic API. In this situation, you could also achieve this by using other types of building blocks that in the background use the same mechanisms for data access, but use the tooling that you are maybe more familiar with. So again, we have a consumer of the data or another service, machine to machine, that needs to get this data, but would assume a mechanism like a, let's say, REST API, depending on the data. So they would go to an API gateway quite normally. They would, again, use IAM to say, hey, I'm here, it's me. Forward this to, let's say, a function as a service, which could be Lambda, could also be something different, like a container, if that's more suitable in your scenario. This would then go to the query engine, be able to access the data catalog to see if the query matches the data structures. This, again, would see, is that the person who should be accessing this, and finally go to the data lake. So this is a valid architecture, but here's a little problem that we need to spot. So as I mentioned earlier, these queries can take very long. And if you do this in a synchronous way, it might be that you're blocking your system for a long time, especially in the case of a Lambda, let's say. You would be paying for the processing time. Yesterday we had a very good talk about how to avoid this and go to an asynchronous mechanism. And this is what I'd like to show here in a second as well. Again, these are just examples of what you could do. I'm not saying you should do it exactly that way, but I would assume that everybody has some experience in how to make architectural decisions between different building blocks that they have at their choice. So this example works in a similar fashion. So we start with the consuming user, we go to the API gateway, IAM mechanism, but now we put the request in a queue instead of processing it immediately. And this, again, will invoke, let's say, a function as a service. So this is asynchronous at this point. We are not returning the result immediately to the requester, but at the same time, we can give ourselves a bit of time to process this. So next, we again go to the query engine and can run against the data catalog. It will again check if we have permissions to access the data we want. It will go to the data lake. But instead of returning this right away to the client, which it can't because it's at this point detached from the original request, it will put the result into a temp storage, let's say. And there it will send a notification. So, S3, for example, is able to emit events when a change in a bucket happens. This could be forwarded to an SNS topic, which again would emit an HTTP event to your consumer outside of your core data system. And then finally, that consumer would be able, after a few minutes or even hours, to retrieve the data and do what they need to do with that, for example, for machine learning purposes, for business intelligence, or any other purpose that they may have. So when we say machine learning, this is one of the first examples that you will see. So, everybody's talking about generative AI these days, and of course, you need good data for generative AI as well. But I want to show an example from a space that is more traditional machine learning, where we still see a lot of data use cases. So in this scenario, you would have multivariate data, so data that is multidimensional, and we want to use this for predictions. And this is one of the cases where we can use large amounts of data to detect patterns and predict, let's say in this case, the behavior of telephone company customers by saying, okay, we have seen that when customers have these usage patterns, they are likely or not likely to leave our company. So what you would do then is you would use a larger chunk of the historic data that you already have for training this model, because you already know the outcome. You already know what you've seen in the last column, that the churn, so basically leaving your company, is true or false based on the pattern of usage. And then you can, if you have identified that pattern, you can use future data in order to predict the behavior of users with a certain degree of certainty, right? So this is a typical use case that you can do with big data or data analytics, in this case, machine learning. This is very useful for many organizations, but at the same time, it requires a lot of work and some special skills in the area of ML engineering. So what many organizations these days use, and which is also very well accessible to an engineer with less data engineering experience, is a business intelligence system. So what you see here is a screenshot of Amazon's own system called QuickSight, and it does things that you are quite familiar with. First, show a graph of data. In this case, over a long period of time, so I think it's about several years in this case. And this is what I meant by historic data. It doesn't mean it's expired or stale. It just means the terms of time we can look at are extremely long. And what this allows us is not only showing the data and letting the user make assumptions or draw conclusions from it, but we can actually use things like anomaly detection. We can see in this data that there are some patterns that indicate that something has happened which is not normal. And this is what it allows you, what you get if you use large amounts of data with fine granularity, that you can see a certain corridor of data, and when data points or chunks of data go out of that corridor, that there's an anomaly. And that has immense value for an organization, because you can go back and see what has happened there. What you also can do is with that is detect trends. So even if we are looking at historic data that may reach several years back, You can use the data in order to see how the development in your organization is. You could see, is there a growth or a decline or a stagnation of a certain data dimension? You can correlate this with other data and see, is there an influence on the data I have here with other data? And that requires you to collect that data and pre-process it in a way that you can constantly analyze it. But still the question is, why do we analyze data? And this is the point where you ultimately would wonder what is the value of all this. Because as I mentioned, it's costly for the organization, it's costly to build, it's costly to run. So why would an organization want to do that? And the reason is ultimately data-driven decision-making. So these are metrics. In the blue area, probably most of those are familiar to you. But other stakeholders in the organization also need data. And I hope that they are making data-driven decisions and not just the CEO comes in and just makes the decision for everybody based on gut feeling. So the business function in the organization, the product function, sales, marketing, everybody ideally would be using data and certain metrics in order to make decisions. And the metrics are based on these data. So the value that you can create for your organization by building such an analytics system and providing a front end to that is that you enable the non-technical functions in the organization in their domain to make data-driven decisions. So this is the value that you get as an engineer. It's not just an exercise in taking some service and plugging it together, but it is enabling your organization to be data-driven and making conscious decisions based on that. So there has been a lot now in terms of technologies that I've mentioned, and probably for most of you it would be hard to just go home and try this out. So here's something that you can use in order to get more hands-on with that, get a deeper understanding. So the first thing I'd like to give you, and I'm going to share this in a second, is a series of YouTube videos that goes through building such a data lake step by step. So you can follow that. You will see it, well, in this case, in the AWS console, and see how you would set this up with Glue, how you would get the data in, how you can create the access layer, and ultimately how you can consume the data in order to build your analytics solution. And secondly, again, AWS specific, there is a whole workshop that you can use in your own AWS account in order to play this through hands-on. So you really have a feeling how these tools behave, and you can modify them, you can try things out in this kind of workshop format. It takes several hours, depending which path you choose. There are several options. It doesn't cost very much. There's just one building block where you create a Kinesis stream and it pumps data, so be sure to remove that when you don't need it anymore. But otherwise, that's a relatively cheap exercise to get hands-on experience with the tools I just demonstrated or just shown to you, and you get this hands-on experience. So feel free to check this out. I'm going to share links in a second. And then you could consider going to your organization and asking what kind of decisions do we want to make based on data. Hey, salesperson, hey, business person, hey, marketing person, what are the decisions you have to make? What is the goals you want to achieve? And what kind of data would help you to answer the questions that you have? So under this link, you will find these both of the sources I just shown to you. You will find lots of other links that show you more details about the services that I just explained. There will be a link where you can get in touch with me via LinkedIn. There's also a little survey, so if you'd like to talk, please take 30 seconds to fill that out and give me feedback. And otherwise, I'd be happy to hear from you if you try this out and have success with that. Thank you very much.
Thank you, Alexander, for coming. We have a number of questions. Let's see. Okay, so even if it's a very basic one, but some people seem to be confused, can you explain in a nutshell what's the difference between data lake versus data warehouse? Because some people
that's a very good question, and it's indeed confusing because it sounds very similar. So data warehouse is, you could imagine more like a SQL database. So it has a schema and is very well suited for structured data. And historically, organizations use data warehouses as to push every information into that warehouse. into a structured schema, but it requires that the source systems already have knowledge about the internal schema of the data warehouse. The advantage is, of course, that you don't have to do all these transformations, and you can consume from the warehouse itself. So data warehouses are still a valid building block in the data architecture. It's just used for a different purpose, like structured data and data that don't change very often, because that would mean a schema change, as opposed to a data lake, which is more flexible in terms of structure and data change.
Okay. So some people, well, it's AWS, so people are concerned about costs, obviously. Any advice you can give in terms of like monitor and control costs with data lakes, because it can obviously expand very quickly.
Yes,
and
very
can
good.
be a good one.
So first, it's a matter of architectural decision. So one thing I should have mentioned within a talk, so thanks for the question, is S3 will be a cost factor for you. So you can use standard S3, obviously, but you can also, for these 3 buckets, use different types of storage tiers. For the bronze bucket, which gets written data sometimes, but not many reads, you use something like infrequent access. For the silver bucket, you can even use infrequent access one zone. And for the third bucket, which also just needs a lot higher read rate, but also not a higher durability, you would use a storage tier like Express One Zone. Of course, then in terms of monitoring, the typical tools that you have at your hands, we have heard lots of details about how to use CloudWatch yesterday, but you will also see integrations with third-party vendors to monitor the cost and the performance.
And related to the usage of S3, people are asking like, okay, but isn't this prone to data duplication, and then how you can kind of prevent that or at least mitigate that?
That's also a very good question. So why do we have 3 buckets here? The important thing is that you want to keep the data that you ingest for a long period of time, and data will change. So the source data systems will change their data structures, and you will have to reprocess it every now and then. So you will have to have this data and then have it in a secondary way for the analytics. You could go with 2 buckets just and do the transformation there as well. It really depends on the change rate, and if it's more frugal to have an intermediate transformation, because it only happens every now and then have the semantic transformations more frequently through a third bucket. I've even seen 4 buckets where you have a pre-filtering for PII, but again, it depends on the architecture you choose to build.
Okay, and they're asking like, when you go row-based versus column-based permission, does it affect there's a massive difference with the speed of the process itself, or?
That's a good question. I haven't measured that, but the thing is, it's completely different purposes, right? So column-based really means certain data dimensions are excluded from access, whereas in a row-based approach, or the function of the row-based authentication is just, I want to exclude certain data fields, but across all the columns, or as a cross-section of those. And you will need both, so it doesn't make sense to compare one with the other.
All right, and I think it covers most of it. Thank you very much. You have some things over there, if you want to advertise.
So for those who like AWS, I've left a few stickers here. So after the next talk, please not now, but
please don't rush now. We will leave them there, so and don't fight for them. All right, thank you very much, Alexander.
Thank you.